take a look at some properties of limits. We've got a couple properties already listed out. And what you're looking at, the limit as x approaches a of c is equal to c. When we take the limit of something, we could think of this as an equation, y is equal to c. Now that's y is equal to c. C is going to be some constant. We know that that's just a horizontal line. And no matter where you pick the a value, if I pick it right here, all of the y values are approaching that same value. If I pick my a value right here, all of my y values are approaching the same thing. No matter where I pick my a value, the y value is going to be the same. And it makes sense because the y value, it's constant. It's always going to be the same. So the limit of a constant is the constant. The limit as x approaches a of x is equal to a. In this case, your equation is y equals x. And we know what that graph looks like. That's a nice graph that comes right through with a slope of 1 passing through the origin. Let me see if I can pass it through the origin, though. With a slope of 1. And no matter where I pick, here we go. No matter where I pick my point, if I pick my point right here, if this is my a value, if the y value is the same thing as the x value, if the x value is a, then the y value also has to be a. No matter where I pick that, the x value and the y value will always be the same. That's what the equation says. And the last one says y is equal to x to the nth. Is the problem that we're looking at. Now, if n is a positive integer, we know that that's going to be some kind of could be a parabola, could be a cubic, could be a quartic, could be a quintic. We know there's going to be no skips, no jumps. There's no asymptotes. There's nothing crazy going on in that graph. And no matter where I pick my value of a, the y value is going to be that a to the nth power. No matter where I pick it, there's no skips, no jumps. It's almost like I'm just allowed to do a direct substitution. Now we can go do a couple more properties with that, but let me jump to an example. So I'm going to take the limit as x approaches 2 of 2x plus 5 divided by x cubed. If we look at what those other properties said, we almost want to say, well, if this is my y equals 2x plus 5 divided by x cubed, I know that everything around 2, this graph is okay. There is an asymptote on this graph at x equals 0, but I'm not really worried about that. I'm going to be close to 2, which means that all the y values should be close to 2 times 2 plus 5 over 2 to the third. And if you go ahead and plug that into the calculator, if you look at all the values that get closer and closer and closer to 2, we'll see all the y values getting closer and closer and closer to 9/8. Kind of nice. Now, something that could be done with this expression. The limit is kind of sneaky. It can get into a lot of stuff here. I know that limit, I could rewrite that limit as the limit as x approaches 2 of 2x plus the limit as x approaches 2 of 5 divided by the limit as x approaches 2 of x cubed. And if I use those properties that I just had written above, sure enough, I end up with the same thing. 2 times 2. The limit of a constant is just a constant, and I can do my substitution there, 2 to the third power. It almost is like that limit is distributing in, but I'm not going to call it a distribution, but it does go into every piece in there. It's kind of a sneaky little thing. Now you're going to use that idea of that limit going into everything or breaking apart or rewriting that limit expression. We're going to use that when it comes time to look at a couple different proofs and a couple different exercises. But that's kind of a useful tool to show how we can split everything up and do a quick rewrite.